Good morning. In this lecture video, we are going to cover three basic laws. The first one is Ohm's Law. In this Ohm's Law, first we are going to see the statements of Ohm's Law and expression in Ohm's Law, and finally we are going to plot a graph between voltage and current. And in the end, we are going to use Ohm's Law to calculate different parameters across an element resistor. And next thing we are going to see is Kirchhoff laws. Kirchhoff laws are of two types. The first one is Kirchhoff voltage law, and the second one is Kirchhoff current law. To the first one, in Kirchhoff voltage law, we are going to see the statement of Kirchhoff voltage law, and we are going to apply Kirchhoff voltage law onto a simple circuit. And finally, we are going to see the conditions or the sign conventions that are need to be followed while applying Kirchhoff voltage law. And in the end, we are going to take one example and apply Kirchhoff voltage law by using those sign convention. Next one is Kirchhoff current law. In Kirchhoff current law, first we are going to see the definition of a Kirchhoff current law. There are two definitions for Kirchhoff current law. We are going to see both of them, and we are going to apply Kirchhoff current law to a basic circuit, and then we are going to see the sign convention that are need to be followed while applying Kirchhoff current law. And in the end, we are going to take one example and apply Kirchhoff current law for that particular example. First one, Ohm's law. Ohm's law states that current flowing through the resistor is directly proportional to the potential difference across it at constant temperature, which means we are going to place the resistor at a constant temperature and observe how current react or how current respond to a change in applied voltage. We are going to apply voltage across the resistor, and we are going to observe the current. In this observation, we observe that as we increase the voltage, the current through the resistor is getting increased. So we can conclude the current through the resistor is directly proportional to the applied voltage across the resistor. If you add the proportionality constant, then the current expression is equal to I equal to V by R. We can rewrite the expression as V equal to IR. So the statement of Ohm's law is the current is directly proportional to the applied voltage at a constant temperature. The final expression of Ohm's law is V equal to I into R. If you observe, we performed the experiment at a constant temperature. Reason for this one is if you increase the temperature, due to the rise in the temperature, the resistance of the resistor will get increased. As resistance gets increased, R value is not anymore a constant. It becomes the function of a temperature. So at variable temperatures, you should not apply Ohm's law. This Ohm's law is only applicable at constant temperatures. Moving on to the graph between the voltage and current, voltage and current relation. What we are going to do is, now let us take a simple resistor R. Let's suppose say the resistance value is R, and we excited this resistor with a voltage source V. Let's say a current I is flowing through the resistor. So practically, to measure the current I, we need some sort of a measuring equipment. That measuring equipment is called as ammeter. So we are going to connect an ammeter over here, such that we will get the current values. Similarly, to know the voltage values, we need other form of external measuring equipment. That measuring equipment is called as a voltmeter, which measures the voltage is connected across the resistor. Now our aim is to draw a relationship between voltage and current. Now what I am going to do is I am going to take voltage, applied voltage as a reference, and I am slowly going to increase the voltage and measure the current readings. So let's suppose say the applied voltage V equal to 0. As a voltage is 0, the circuit is unexcited, so the current in the circuit is 0. Let's suppose say I increase the voltage to V1 and the current flowing through the resistor be I1. For a V1 voltage, the current is I1. The corresponding point will be over here. Similarly, for a V2 voltage, let's suppose say current I2 is flowing through the resistor, then the corresponding point will be over here. If I go on increasing the voltage and measuring all the corresponding current values, you will get a points in this particular way. So if you join all these points, we will get a straight line. The observation you can make from this graph is that the current is linearly proportional to the voltage and the slope of the line is equal to 1 by R. If we perform the same experiment for a higher value resistor, then the slope will be less and you will get a graph in this way. If I perform the same experiment with a lesser value than the R, then the graph will be in this particular way. As slope is inversely proportional to the resistance, as we increase the resistance, slope decreases. As we decrease the resistance, slope increases. Moving on to the numericals. The first question, find the current through the resistor if applied voltage across a 1 kilo ohm resistor is 25 volts. So he is saying that we have a resistor R. So voltage across a resistor is 25 volts. We don't know the current I through the resistor, and resistance of the resistor is 1 kilo ohm. If you apply Ohm's law, which is V equal to IR, where V is the voltage or potential difference across the target element, this is the target element, the potential difference across the target element is 25, so it is 25, which is equal to current through the target element. Here the target element is 1 kilo ohms, the current through the target element is I, that is a variable we need to find. So I into R, and R is the resistance of the target element. So the resistance of the target element is 1 kilo ohm, which is 1 into 10 to the power of plus 3 plus. If you cross multiply, the current expression is equal to 25 milliamps. 25 milliamps. Moving on to the next question, find the resistance of the resistor. If the current through the resistor is 1 milliamps and the potential difference across the element is 10 volts, we have a resistor. The resistance of the resistor is let's suppose say R, and the current through the resistor is 1 milliamp, which is equal to 1 into 10 to the power of minus 3 amps, and the voltage across the resistor is 10. If you apply Ohm's law, V, which is equal to 10, 10 equal to I, current through the resistor, which is 1 into 10 to the power of minus 3 into R. So the resistance value R equal to 10 kilo ohms, where 1 kilo equal to 10 to the power of plus 3. Moving on to the Kirchhoff laws. There are two Kirchhoff laws. The first one is Kirchhoff current law, Kirchhoff voltage. First one, KCL. KCL stands for Kirchhoff current. Moving on to the statement of Kirchhoff current law. The algebraic sum of currents at a node is equal to 0. We have one more statement, which is the sum of entering currents is equal to the sum of leaving currents at a node. Now if you observe in our statement, we have a term called node. Now what is a node? Node is a common terminal where two or more elements are connected. If you see any intermediate junction between the two elements, either it can be a passive element or an active element, or a combination of active element or a passive element. The junction or a joint where the active or a passive or a passive elements meet is called as a node. The condition for a node is at that particular point there should be a two or more elements that are need to be connected. We have one more term called as junction. Junction is similar to that of a node, but junction is a common point at which three or more terminals are connected. Suppose say if we have this type of a circuit, if you observe at this particular point two elements are connected, so we can call this one as a node. It satisfies the condition greater than or equal to 2, but we cannot call this one as a junction because only two elements are connected. Two elements are connected. To call this one as junction, we need three or more elements that are need to be connected at this particular point. Let's suppose say one more element, an active device connected over here. Then we can call this one as a junction, as three elements are connected. Two passive elements, one active element. We can also call this one as a node, as a condition for node is greater than or equal to 2. It is greater than 2, so we can call that one as a node. So back to the Kirchhoff current law. Kirchhoff current law statement is that the algebraic sum of currents at this particular node is 0. So the meaning of algebraic sum is it is not a simple addition of all the current values. You need to also consider the current direction. You need to also involve the current direction in the equation. To involve the current direction in the equation, we need to follow sign convention. This is a sign convention. If this is a node, if current is entering the node, generally we will consider that current as a positive current, and if current is leaving a node, we will consider that current as a negative current. So if we add all these currents by involving the direction into the expression, then it is called as a algebraic sum. Now as this is an entering current is treated as a positive, so plus I1. Let's suppose say this is I1, I2, I3. Similarly, as this is an entering current, I2 is also taken as a positive, and whereas I3 is leaving the node, then it is considered as a negative. So if you see this example at this particular node, I1, I2 currents are entering. So we took I1 and I2 as a positive, but whereas I3 current is leaving the node, we took I3 as a negative. So this is with the Kirchhoff current. We have one more Kirchhoff law statement, which is the sum of entering current is equal to the sum of leaving current at a node. Simply by adding I3 on the both sides in this expression, we will get this expression. If you observe, the entering currents are I1 and I2 is equal to the leaving current I3. So from this statement, we can say the sum of entering currents is equal to the sum of leaving currents. Moving on to the problems. Here we have a node. As there are 6 elements connected at this particular point, we can call this one as a node. Starting with the I1. I1 is an entering current, slow, so it is taken as a plus. As I2 is leaving, the next term is minus I2, and I3 is entering the node, so plus I3. I4 is also entering the node, plus I4. I5 is leaving, so minus I5. I6 is leaving, so minus I6. Finally equal to 0. This is a Kirchhoff current law expression for this particular circuit. Moving on to the next Kirchhoff law, which is Kirchhoff voltage law. Now, the statement of a Kirchhoff voltage law is that the algebraic sum of voltages in a closed loop is equal to 0. In the Kirchhoff current law, we applied Kirchhoff current law at a particular node, but whereas Kirchhoff voltage law is applied in a loop. If you see any closed circuit, you can simply apply Kirchhoff voltage law to that particular loop. We have a loop, so we can apply Kirchhoff voltage law. So the statement says that the sum of voltages across each and every element in a closed loop is always equal to 0. With the help of these statements, we are going to write down the expression for a Kirchhoff voltage law in this particular loop. Before writing Kirchhoff voltage law in any loop, you need to know the sign convention. As that of a Kirchhoff current law, the entering current is taken as a positive and the leaving current is taken as a negative. Similarly, in the Kirchhoff voltage law, we have certain conditions to be followed while applying Kirchhoff voltage rule or voltage law. The first step is identify a loop. Here we have a loop. If you start from this point, we can reach the same point by choosing a path through V1, R1, R2. So the first condition satisfied, we have a loop. The second condition is that choose the direction. So while analyzing a loop, we will start from a point and we will complete a loop and come to the same point. Either you can go in a clockwise direction or anti-clockwise direction. Choose one direction. Either it can be on clockwise or anti-clockwise. You will get the same results. For this circuit, I am choosing clockwise direction. So clockwise it is. Next thing is assume the current in the loop and represent positive negative terminals for every element in the loop. I am assuming current I is flowing in this direction. You can also assume it in the reverse direction. No problem in that. I assumed a current I1 is flowing in this particular direction. Moving on to the terminals, as longer one is a positive plate and shorter one is a negative plate. This is plus, this is minus. For a passive element, the current entering terminal is considered as a positive. So as current is entering this terminal, this is a positive, this is negative, and current will flow in this direction and also enter through this terminal. This is a positive, this is a negative, and complete the loop. So the third point is assume a current and give the positive negative symbols for each and every element. And the final one is just simply applying Kirchhoff voltage law starting from a particular point. So I am starting from this point. You can start from anywhere in the loop, but I am starting from this point and going in the clockwise direction. You can also go in anti-clockwise direction. So as I am analyzing the circuit from the negative terminal to the positive terminal, which is similar to this one, then the voltage source should be taken as a positive. So plus V1. Moving on to the next element. Here we have a resistor. For the resistor, while analyzing the circuit, we are moving from positive terminal to the negative terminal of a battery. So we should take as minus IR1. We should consider this voltage as minus IR1. So minus IR1 it is. And the next element is a second resistor. For the second resistor, we are moving from a positive terminal to the negative terminal of the resistor. So minus IR2 equal to 0 according to the Kirchhoff voltage law. So this is the expression we got if we apply Kirchhoff voltage law, which is the algebraic sum of voltages across each and every element is equal to 0. So with the help of a Kirchhoff voltage law, if we know the voltage, if we know R1 and R2, we can find current I. So with the help of Kirchhoff voltage law, we can find different parameters in the circuit. Moving on to the example, we have a circuit where we have a 2 voltage sources and 3 resistors. The first point, choose a loop. We have a loop, and the next is choose a direction. I want to go in a clockwise direction and starting from this particular point. While I start from this point, the first element I got in on the way is a voltage source. While applying KVL, we are moving from a negative terminal to the positive terminal of a battery. So plus V1 it is. Plus V1. And for a resistor, we are moving from positive side to the negative side of the resistor. So minus IR1 it is. And for V2 voltage source, we are moving from positive plate to the negative plate while analyzing. So minus V2. Similarly minus IR2 and minus IR3.